found that I missed one before the previous lecture. I said I'm going to modify what I just said about the 7-qubit code. So I'm going to talk about this for the first part, and then we'll move on to the service code. So go back to your notes on 7-qubit code. So there are 6 stabilizer gates. So M0, M1, M2, and N0, N1, N2. And these are about X gates, and N is about Z gates. And we have 7 qubits, and we define that it is initialized by taking measurement gates or syndrome measurements on this 7 qubits initialized at 0 ket by applying these 3 syndrome measurements. 1, 2, and 0. So I just used the projection operator. So I'm going to redefine what that is. The projection operator PA. So if A is an operator that satisfies this equality, then we define the projection operator to be this. So more precisely, we put 1/2 just to make this operator to satisfy certain condition. But if you want projection operator preserve the norm or strength of the qubit, then sometimes we might modify this coefficient over 1/2. So for example, let's look at the. No, this is right. Yeah, a squared equals 5. That might make sense, right? So, no, this is right. So this, so basically, let's see. Square equals 5. Yeah, well, let's see. So I got confused with the projection matrix in the linear algebra. So what we have here for M1, let's say M0 case, so P M0, what happens when I apply this to, let's say, 7 qubit, 0, 0, 0, 0. And what I'm doing is, suppose that after I run through this circuit, M0, so here we have 7-qubit system, and here we have this measurement qubit, and I take a measurement. And suppose that I get 0. So what happens on the 7-qubit is same as applying this operator on 0, 0, 0, 0, 0. Why? Because so we have plus M0 here. So if we have 1 instead of 0, then it would be same as 1 minus M0. So, and then once we have this, we have 0 ket by just applying the distribution rule. We have 0 ket and M0, 0 ket, and these are 2 different base states. And still we want the same strength, qubit states of unit length, unit strength. So we need a modifying coefficient for that. So then we need 1/√2 here. So this is when the measurement outcome or syndrome measurement equals to 0. So that's basically why we kind of applying and consider our state is changed by applying these operators. This is kind of complicated case, so we can give an example here. I think I did it, but I'll do it again. So let's say we have px applying on 0, right? So what I'm doing here is Hadamard, C0, Hadamard, and measurement. And I measurement outcome is 0 here. Then it's same as 1 plus x 0. So what is it? Plus. Right? So this plus cat is plus one eigenstate of x gate. Right? So that coincides our setting here. So whenever we have syndrome measurement and have 0, that means our control qubit or target qubit is stabilized as plus one eigenstate, and if you have minus, if you have a 1, let's say what happens if we have 1. So that means overall this target qubit is stabilized as minus cat, which is minus one eigenstate of x. Then it's same as putting minus here, right? So you get minus, then the 1 is not constant one, it's the identity operator. So 0 cat minus 1 cat, which is minus 1, right? So it coincides with our result. So basically when we say this, then we kind of initialize all 7 qubits with 0 cat and apply syndrome measurement with these 3 gates, M0, M1, M2. And adjust our strengths by multiplying some constant. So this is considered as logical 0 or 0 cat. So kind of, because we assume that the 7 qubit encodes one logical qubit. So this serves as 0 cat in a real physical single qubit. And we also define 1 cat, which is the opposite base, to be 1 over 0 over 2. The same thing, but we simply apply this to 1, 1, 1, 1, 1. So we have x bar 0. Okay. So here, x bar means x0 up to x6. Okay. So instead of 0, 0, 0, 0, 0, we have set 1, 1, 1, 1, and then run through all the same circuit again, and it's going to be, and suppose that we read the measurement outcome of all 3 syndrome measurements to be 1, then we call it this 1 bar. But ideally what happens if you really want to implement your 7-qubit code, you don't expect that outcome always turns out to be 1, 1, 1 or 0, 0, 0. Right? It could be 1 out of 8 chances. And what really happens is just start whatever you got. So instead of getting 0, 0, 0, let's say you got 1, 0, 1. Then, and you want that to be your 0 cat state, logical 0 cat. Then you just assume that this 1, 0, 1 on the first measurement outcome, you just consider 1 to be 1 to have the same role as 0. So 0 is 0, and 1 is kind of assumed to be have the same role as what happens if we had a 0. So in that case, if you have this as a measurement outcome, your syndrome measurement, then your 0 logical qubit will be, theoretically, if you write down the formula as an operator, then it's going to be minus m0. So suppose that this is 0, 1, 2, and 1, and minus m2 applied on 0 cat. So it really depends. In the practical application of this depends on what your measurement outcome is. But our situation is ideal that we always get 0 in some sense, which means that our quantum state is already, before we took the syndrome measurement, already stabilized as plus 1 eigenstate of every syndrome measurement. So anyway, so our we left the point where we want to explain that there is a Hadamard gate, the logical Hadamard gate for the 7-qubit code, and this is simply defined to be H0 to H6. And we're going to show that by proving that this H bar, which is just normal gates acting on 7-qubit, when I act that on logical 0 cat, it's going to be same as this. And if I apply that to here, so this is not 1, 1, 1, 1, and this is not 0, 0, 0, 0. So just remember that this is some complicated, maybe entangled state, consists of lots of base 7 qubit states. And if I show that these two are the case, then this H bar is logical Hadamard gate acting on these two, logical cat 0 and logical cat 1. Okay? So how do we show that? So first of all, let's observe that this zero, logical 0 and logical 1 are two orthogonal states. So if you look at this inner product, what is it that you have? Logical 0 cat bar bra. So it's a dual of logical 0 cat, right? So we're going to rewrite this as dual of this state by just reverting everything. Cat becomes bra, and all the operator, you take a dual or kind of permissions dual operator to this, and when you do that, we change the order of this operator. But actually, these operators are all commutative, so we can just skip the order. So anyway, so this is the bra of 0 cat, right? And then we got the coefficient. And then here, if I take the bra, well, these are just multiple of x gates. The dual of x gate is just x, of course, and dual of identity operator is just identity operator. So these are the same thing when I take the dual. So, and also I don't need to change the order, but ideally I have to change it. But it's the same thing. That's what I get here. What we do is we want to show that this is 1, and also when we change the order is 0. So what time? Oh, sorry, not 1. It's 1 over 2. So once I show this, then since these are orthogonal states, there is no other case that this has to be of this form. So I need this. So I need this condition, but let's assume that we have this already. And I can just do one of these. Let's do the easiest part. The rest of it is just similar. And okay, so here we have the same formula here. So 0, 7, bra, and 0, and 2, h, and 0, and 2, 0 here. And then we're going to, so Mervyn did a little bit of a trick so that what happens is if you, let's see, switch the order of Hadamard gate and the M gate here, then since M gates consist of X gates, so it's like changing the place of Hadamard and X gate. So whenever you have Hadamard X, you can write it as Z Hadamard, just for every single qubit case. Therefore, it implies that whenever you have MI, applying the Hadamard, so whenever you have a Hadamard on ith qubit in MI or jth qubit in MI, then it becomes the Z qubit, Z gate on that jth qubit times the Hadamard. So it's going to change into the Z gate stabilizer Ni times H bar. So if I apply this, let's apply that to here, these two terms. So H bar and this M part, and we have 1 over 2, 3, 7, 0. And then Mervyn also did a clever thing. So here we exchange the order of this N stabilizer and N stabilizer. So they are commutative because there are only 4 gates for each of these stabilizers. So even if the switching the order of X and Z gates gives you minus sign, there are 4 minuses. So every time you do this, you don't change the sign. So we have N0, N plus 2, and M1 plus N2, and 1 plus M0, 1 plus M2, H bar, 0 cat here. And then what? So we again switch the order of H and this M. So you get 1 over 2, 7, 0. 1 plus N0, 1 plus n is about what? Z gate, right? Z gate doesn't do anything on zero cat. Okay? So suppose that we take this first part as a bra, and these parts. Is a bra take from the dual of the cat state where we apply 1 plus n0 to 1 plus n2 to 0 cat. So it's the same thing because 0, whenever we have a 0 cat on each qubit, when you apply z gate, it's just the same thing. It's plus 1 against it already. So it's going to be just the same 0 cat when you apply this to the 0 cat. And you take the bra, so we're going to be same as just bra 0, right? So let's say we done this. We reduce this down to 0 bra. So we used up the half of this, the coefficient. And then what? We have Alamart, and this also is 0 cat. Right? So we used another half of this coefficient. So what is this? So we have the Alamart in wait, so we have, at some point I need to be careful about the signature here. Let's see, which is here. Let's see, so 2, 2, 2. Yeah, so when I apply these operators, so let me just be careful about this. The tedious calculation is missing on both, so I'm just trying to make it concrete. So here, what I'm trying to do is suppose that I have n0, n2 on 7, and every time I apply this gate or its operator, I get twice of this, because the n0, n1, n2 applied to 0 cat is 0 cat. So I get 0 cat plus 0 cat. I get twice of 0 cat here. So I have a 3, so you get 2/3 of 0 cat. So the red part, the whole entire red part, is now replaced by 2/3 0 bra, okay? Because of this 2/3. And then Hadamar. And then do the same thing on the next part. So we get square of this and 0, right? So canceling this out, we get 2/3 of this. Now it's get interesting. So what is this? So when we apply the Hadamar gate on 0 cat, we get plus 4, right? We get superposition of all the base state with the same coefficient. So among them, we only want the 0, 0, 0, 0, 0, and take the inner product. So we just take the coefficient of the superposed state of the 0 cat, right? So we have 2/3 and 0 here, and so among. So what is the coefficient for this? So we have 2. How many of them actually? So we have 2, 7/2, right? 7/2 sum of I from 0 to 2, 7 minus 1 of I7, right? So this is the Hadamar applied on the 0 cat here. And we have a canceling out with this and this, so we get 1/2 to the 1/2. And among these, I only need when I equals to 0, when you have 0, 0, 0, 0, 0, and the inner product is just 1, right? So we get this, right? So where we started, so we started here. So you can do the same thing in here. So only difference is that you're gonna have x bar somewhere, and you can move around this x bar to make x bar square, so it will cancel out. So it basically becomes the same notation, same computation as before. And for this part, now yeah, you can keep your x, but at the end, x will just change this, everything x will, well, let's try this. Let's see how it happens. It's curious. So what is this? The same thing where we have 2/3. We have 0 here, and 1 plus m0, 1 plus m2, and 1 plus m0, 1 plus m2, x bar, 0, what, h here, h bar here. Okay. Okay. Let's see. I can see. So you have to be careful about this, right? So I can move around, moving around in between this h and m part in these chunks, just as what we did here. So we have 1/2 square cube and 0 and n0 and n2 and 0 and 2 x bar 0, 7. Okay. And then what? I'm going to move x bar up to here. Is it possible? Yes. Because every time I change the order of ni with x bar, there are 4 z8 inside of xi, right? So there are going to be 4 minus 1 applied, but it's becoming plus. So it's I can move around x bar without changing n to m. So it's still n. So we have, this is 1/2 and 7, 0, 1 plus n0, 1 plus n2, Valdemar x, 1 plus n0, 1 plus n2, 0 can here. Okay, so we do the same thing as before. So we have 7, 0, n, Valdemar x, and what? 0, 7, right? So now this becomes, not gonna erase this. So this becomes 7. Let's not forget about this. 2/3 and 0, h, 1, 1, 1, 1. Okay. Right. Let's see. So now how do we get 0 here? How do we get 0 from here? Let's see. Wait, so what? I didn't want 0, right? I want -1. Sorry. I want this. Sorry. So I want the superposed state of this. So when I apply this to, let's see, h0, I want the same 1/√, coefficient. And also if I apply 0 on here, I also want √2. When I apply 1, 1 here, 1, 1 here, I want -1/√2. Sorry, so this is the wrong thing that I was trying to prove. So, yeah, so let's see. Let's suppose that I just want to show that this is true, and I need to change this to 1. And here I have x bar, right? So I can move around, doing move around here, okay? And once I did this, I'm going to have x bar inserted here, and then here x bar again. And what happens is we have here again 1, 1, 1, 1, 1, 1, 1, right? So imagine what we are having here. So we have 1/2 and 1, 1, 1, 1, 1, 1, and we have inner product this bra with coefficients are something, it's not always positive, right? So we have I, 7. But what we want is just, I want to take the base state, which has 1, 1, 1, 1, 1, 1, right? So there's only one. There's only one of them, which is when I equals to 2 to the 7 minus 1. So what is the coefficient in that case? So when you want to get 1, 1, 1, 1 among this superposed state that is given by the tensor product of minus cats, 7 minus cats, then you just take the minus 1 cat for each qubit I, right? So then you get minus 1 comes with it. So we get 7 qubits, so we have minus 7 minus 1s. So this, and then 7 minus 1, and 1 over 2. Sorry, at some point I need to change it to 2 to the third, right? So when I change this, it's 1 over 2 thirds, it's 2 thirds. And then these two cancels out, 1 over square root 2, and the minus 1 comes out. Right? So now we get minus 1. Yes?
Your conclusion is this value is 0 is 0 is the same as the 8 times 0 is 0. So I think it doesn't make sense.
Or which here?
Upper
Here?
0 is 0, yes.
So we get 2 to the third square here, so we cancel it out to get 2 to the third.
But the original was just 0.
Yes, 0, 0. Yes. So let's just review the computation here. So 0, 0. We get this coefficient by definition, and we just multiply to 1 over 2 thirds. And we didn't do anything about the coefficient. We just move around our operators, and this is here. And where this red part come from? It comes from this computation
Yeah,
here.
I know. But
Yes. So I collapsed this part and also this part.
I want to know what is the original vector, original of the. So is it just original 0 is 0?
This 0 bar
Yeah.
is not 0, 0, 0, 0.
It's I don't know. I mean, is it the original 0 is 0?
What do you mean by original 0? This 0?
No, just bracket, whole bracket.
Whole bracket.
Yes.
Okay. What do you mean by original?
And just that bracket.
This one?
Yes.
So this thing is same as this thing.
I think the question does not match.
Okay, so we start from coefficient 1. This comes when I expand this by definition. Okay. So and then this part, I collapse this part to get this. Right?
So
and I took the broad.
yes.
So we get this one of these 2 to the third.
You got the coefficient 8.
Yes. No, actually 8 squared.
8 squared. So divided by 8. So
Yes. So we got 8.
conclusion is 8.
Yes. So yeah. So this equals to 8 times of this.
So it is 0, right?
What is 0?
So the whole bracket becomes 0, right?
No. This 0 bar is not 0.
Yes, I know, but the value of whole bracket becomes 0.
Why? This thing is not. So just this 0 bar is a notation of some complicated states. Okay, the 0 bar is not 0 cat. It's a logical qubit, logical state, logical qubit state, and it consists of superposition of physical states of 7 qubits. But we don't know. I mean, it's too complicated to write. Okay. Any other questions? Okay, so I'm going to briefly review about the surface code, and I'm going to show you my simulation on the surface code to make a visible presentation. So let me give a diagram again. So the surface code consists of stabilizer and data, right? So data, stabilizer, so X. I'm going to make a smallest possible surface code here. So we have set X. Not really good surface code, but I think that will do. Okay, how many stabilizers? So let's count the number. There are 4 stabilizers, okay? So what does stabilizer do? Stabilizer is measured first, and the measurement outcome of the stabilizer gives the signature. So the signature consists of 4 tuple of numbers, either 0 or 1, right? So what does this 0 and 1 means? It means that if X is 0, then the data qubits are stabilized as +1 eigenvalue or eigenstate of this X stabilizer, which means that this X is acting on these 3 data qubit nearby. And when we do the first cycle of surface code, then we kind of have a C0 gate or control X gate from here to here, here to here, and here to here. And same for other stabilizer. When I do the cycle, this stabilizer is acting as control Z qubit, control Z gate on these 3 data qubits and for others. So by the read-off of the stabilizer, we know that these data qubits are stabilized in some sense or collapsed into eigenstate based on its signature, right? So let's count the number of signature or count the number of count the number of possible signatures. There are 4 stabilizer, so number of signature is 2 to the 4. Right? Now, so we have how many base states, or what's the dimension? Dimension of, let me write just random notation here. So let's say I want to find the dimension of a Hilbert space consists of data qubits. How many data qubits are there? 5, right? So I just want to make a Hilbert space of those 5 qubits. So what's the dimension of that space? It's 2 to the 5, right? So now the question is, I have only 16 signatures, but there are 32 possible dimensions, 32 dimensions of the quantum state. Right, so signature, each signature fixes fixes a state about data qubits. But this fixed state, so signature, a single signature, let's say C1, C2, C3, C4, let's label it 1, 2, 3, 4. This gives eigenstate. In H5, the 5 qubit state, right? But this eigenstate lies in an eigenspace. So this lies in eigenspace. And what is the dimension of this eigenspace? How many freedom do you have to move around inside of your Hilbert space, which has the same signature? So there are 16 different signatures, but there are 32 dimensions. So 32 divided by 16 is 2. So each eigenstate is lying inside a 2-dimensional eigenspace of the Hilbert space. Right? So the reason being that is because we initialized our data qubits. I mean, not because of that. I mean, even if it's nothing to do with initialization. So if you have a random state, everything is possible. Maybe the probability is different, but cat 0 and cat 1 are both possible. Right? So that you take a cycle and you run the one cycle and then take a measurement, and there are are 16 possible choices of signature. Right, you just took one, and the data qubit will be some kind of quantum state lying in the Hilbert space, but that lies on the eigenspace of the signature of your readout. And then this eigenstate is actually lies on the dimension 2 subspace of the Hilbert space, because there are differences between these dimensions. So this is actually the important point. So if you have exactly same number of signature and same number of the dimension of your Hilbert space of data qubits, then you have no freedom at all to give any logical gates. So we want to give the we want to define a logical gate on the surface code, and while we are able to measure or detect an error. So that's the catch. We want to give logical x and z on each on let's see, surface code, or not give, define a logical x gate. So I'm not changing, so it's not same as just applying x gate on a specific qubit. So I want to define what logical x must be in order to make this a logical x to act as if it's the physical x gate on a physical qubit. So this logical x or z should not change the signature, because they must not be detected as an error. That's the important part. I think this also applies to 5 qubit code and 7 qubit code we observed before, but the thing is, every quantum error correction code not only detects an error, it also comes with logical gates. And these logical gates are not an error. So that means when I apply this logical gate to any quantum error correction code, it should not be detected as an error, right? So which means that it should not change the signature in the surface code, because if there is a change in the signature, it means that the surface code detected an error occurred in somewhere, right? So how do we make such change? How do we make such difference by not changing the signature? Instead of doing nothing, how can I make nothing happen? How can I make something not happen at all by doing some changes on these data qubits? So here, think about this case. Suppose that I apply that error or Z gates on these two data qubits. Okay. Sorry, this is X. Sorry, 3X. X gates here. Then what happens? So this is not an error. Again, I apply X gate intentionally, and next time, so I apply this X gate on these two data qubits, and next time I apply this surface code cycle, do I change the readouts? Means assuming that there's no extra error occurred, no error occurred whatsoever. If I apply X gate on these two data qubits, does the signature change? No, because X, so suppose, even if you suppose that this X is an error, this X is not detected on this stabilizer, nor on this stabilizer. It is detected on this Z stabilizer because it's an X error, but there are two. So this error kind of changes the readoff of this Z stabilizer, but this one also changes again. So it's gonna cancel out, effects are canceled out. So even if I apply X gate here, there's no change in the signature readout of this measurement gate. So I'm still in the same eigenspace. But then, let's say I have Z and Z here. So what happens here? I don't change the signature, right? The only place I can change is this X stabilizer, but there are two, so the effect of changing the signature cancelled out. So it's gonna be the same signature, same quantum state with the same signature. But the problem is, now we have the data qubit, one data qubit has X and Z gate together, right? But the problem is the order of applying this Z gate, series of Z gate and series of X gate matters, right? So when you, so let me give a name for this, or label this. So let's say this is A, B, C, D, E. So I'm going to define X bar to be X, B, X, E. Okay. And then Z bar to be Z, D, Z, E. So when I apply X bar, Z bar, and Z bar, X bar, does the signature, does these two the same operators? They're not the same. So I only change the order of these gates. So it doesn't matter when the X and Z are applying on the different physical qubits, but it matters when it applies on the same qubit, qubit E, right? So in that case, if I change the order of the application of X and Z, I get different sign. So I have this identity, right? So this X and Z is considered to be logical X and logical Z because it satisfies the omni identity, omni equation that X gate and Z gate must satisfy. But the question is, okay, so is it only X gate, only a logical X gate, or only logical Z gate? So how about, what if I apply X and X here? So suppose that, okay, instead of having X here, I want to apply X on here too. Does it work as an X gate, logical X gate? So suppose that I have X bar to be X A, X B, X C, B, X E. So then, okay, so if I take this as a logical X and this as a logical Z, X Z bar is equal to what? Z bar X bar, right? Because there are two physical qubits coincide at Z gate and X gate, so the sign interchanges twice. So it's going to be just plus. So this does not act as an X gate. How about, okay, so how about this? So instead of having XB, XE, I want to say XA and XD. Yeah, so. And then I take another logical Z, the same thing, ZD and ZE. So, which means that I don't have X here. Right? Does it work as an logical X gate? Yes. So there's no single X gate. There is no fixed logical X gate or fixed logical Z gate. As long as it satisfies the rule of X gate and Y gate and Z gate, it can be used as a logical X and logical Z. So I'm going to draw a bigger surface here from now on. What did I erase? I don't have to erase this. So what I'm going to draw is kind of some kind of zoomed out picture of the surface code. So let's suppose that I extended this kind of lattice of this stabilizer and data qubits to the right and to the bottom here. So then what I get is on the top I have data qubit, X stabilizer, and so on, right? So I'm going to, So I'm going to just put that line as a straight line here. And on the left boundary here, it's going to be data qubit, Z stabilized, data qubit, Z stabilizer, right? So I'm going to write this way. And then, okay, so the next line, we have X, but we don't want to end here. So every time I extend the lattice, I'm going to extend by 2 steps. So the next step of extension is when it finishes with this. It finishes with Z stabilizer at the right. So at the right, I'm going to have a Z stabilizer here. And also I'm going to extend it every time in 2 steps. So the bottom of the surface code will end with the X stabilizer. I'm going to write it here. So everywhere here, there's an X stabilizer on the top and bottom. And on the left and right, there is the Z stabilizer. Kind of imagined this way. And this, the convention is, this is called smooth boundary, and this is rough boundary. Just to distinguish these 2 boundaries. And whenever you have chain of X gates, or let's see, chain of X gates from top boundary to the bottom boundary here. So this is chain of X here, and the chain of Z here. Then it serves as X, logical X and logical Z. Why? Because there is always an intersection. So you see, you cannot start anywhere. We cannot start from here. So whenever you want to find that chain from the left boundary to right boundary, you have to start from the leftmost data qubit, which is on the boundary here, to put Z here, and then follow your path in between the X stabilizer here. So you cannot go Z from here to Z from there. You cannot skip. You always go from data qubit, X stabilizer, data qubit, X stabilizer, data qubit. Okay. So in this case, this is the simplest one, but you can go a little bit detour. So instead of having, let's see, Z stabilizer, X qubit, Z gate, X stabilizer, and you can go to the right, or you can go to the top. So Z stabilizer, X, and Z, X, Z, X, Z. This is also possible. So you can go anywhere like this. You can even go backward. You can do whatever you want, right? So whatever you do, if your Z chain is starting from the left and ending at the right, and if you count the number of intersections with these chains, let's say these chains, some here and here, going here, and take the intersection between these chains and chains of X, right here, going straight through the top to bottom. How many intersections do you always count? You always count odd number of intersections. So whenever you have an odd number of physical qubits intersecting these chains of Z and chains of X, when you take change the order of X, logical X and logical Z, you always get the change of sign. So it also works as a logical X and logical Z. I was supposed to show you the picture, my simulation code. So I'm gonna record a video for this. And by the way, I forgot to mention this. So on next week Monday, I have to cancel the class. So I'm going to, instead of make up the class by uploading the video this week or the Monday class, but there's not gonna be a physical class on Monday. I need to go to hospital. Yeah. I'm gonna explain more about how does this work in the video using my Python code to visualize the surface code.